2024 A-Level Combined Mathematics Paper 1, Part B, question number 15, Part A. Parts B and C of the same question will be discussed in future videos, links in the top right. Part A of this question has to do with integration and partial fraction decomposition. The question says, find the values of the real constants capital A and capital B such that 3t squared plus 4 is equal to capital A times t squared minus 2t plus 4 plus capital B times t plus 1 for all t in the real numbers. It then says, hence or otherwise, find the integral of 3t squared plus 4 divided by t plus 1 times t squared minus 2t plus 4 with respect to t. Now to start this question, the first thing I'm going to do is use the fact that this is true for all t elements of the real numbers to say that the polynomials on the left hand side and right hand side are identical, and therefore the coefficients of t squared, t and the constant terms must be equal on the left hand side and right hand side. What we can then do is to derive some simultaneous equations from this that we can use to find the values of capital A and capital B. Now once we find the values of capital A and capital B, we can then resubstitute, and then in order to get this term right here, what we're going to do is to divide both sides of this equation by t squared minus 2t plus 4 and t plus 1. Doing so, we can see the left hand side will turn into this exact expression, and on the right hand side we'll be left with two partial fractions that we can then use in order to find the integral with respect to t. So to start off, we'll write down this equation. We'll write 3t squared plus 4 equals capital A times t squared minus 2t plus 4 plus capital B times t plus 1. And we'll say for A comma B and the real numbers that we don't know, and all t element of the real numbers, which is the condition that allows us to say that the polynomial on the left hand side and right hand side must be equal to each other. So if they're identical, it means that considering the coefficients, we'll say considering coefficients, the coefficients of the x squared term, or rather in this case t squared terms, should be equal, the coefficient of the t terms should be equal, and the coefficient of the constant terms should be equal. So we can say considering t squared terms, we can also consider t terms, or t to the 1 terms we can say, and we can consider constant terms, or t to the 0 terms. In this case I'm going to write constant terms. So considering first the t squared terms, the coefficient of t squared terms on the left hand side and right hand side should be equal. On the left hand side we can see the coefficient is 3, and therefore 3 should be equal to whatever t squared terms coefficients we have on the right hand side. Now on the right hand side we have a times t squared, which means that a is one of the coefficients, so we have a, but then we also have b times t, which is going to be bt squared, and therefore we have also another b for the coefficient, and therefore the total coefficient of t squared is a plus b. So we have 3 equals a plus b. We're going to call this equation number 1. Now moving on, the next thing we're going to do is to compare the t to the power of 1 terms, or the t terms. Considering these on the left hand side, we have no t terms, which means we actually have plus 0 t terms, meaning the coefficient here is 0. So therefore on the left hand side of our equation, we're going to write 0, and then we're going to consider the right hand side. So for the right hand side, we have capital A times negative 2t here, which means if you take out the t, the coefficient is negative 2 times a, or minus 2a. Now considering the next bit, we have b times t plus another, or times another plus 1, which is going to be b times t plus times 1, which is going to be b times t, which means the coefficient there is b. So therefore we have plus b as the coefficient there, and we have minus 2a, meaning the total coefficient is minus 2a plus b, and that is going to be equation number 2. Now we could stop here since we have only 2 unknowns and 2 equations already, but we're going to solve the third equation considering the constant terms. So for the constant terms on the left hand side, we can see we have only a single 4, so we have 4 equals, on the right hand side we have a times 4, which is 4a, so we have 4a. And considering the other term, since we have b times t already, none of the terms coming from this could be constant terms, and therefore we have 0 constant terms coming from there, meaning the only constant term is 4a, which is equal to 4, and that's going to be equation number 3. Now from equation number 3, we can already see, we can directly get that a is equal to 1. And with that, we can substitute into equation number 1 and say if a is equal to 1, then b plus 1 is equal to 3, and therefore b must be equal to 2. So hence we have found the values of capital A and capital B. Now what we can do is to take this original expression and substitute in capital A and capital B, and then try to divide by t plus 1 and t squared minus 2t plus 4 in order to get this thing right here in terms of partial fractions. So going down, if we write that down, we can see that therefore, we can write, therefore, 3t squared plus 4 on the left hand side is equal to a times t squared minus 2t plus 4, which will be 1 times that, which is just t squared minus 2t plus 4 plus, and then we have another term. That term has b equals to, and it is 2 times t plus 1. So we can write 2t times t plus 1. Now what we can do is to divide everything by t plus 1 and t squared minus 2t plus 4. So if we do so, on the left hand side we're going to get 3t squared plus 4 divided by t plus 1 times t squared minus 2t plus 4. Now considering the right hand side, when we divide, this thing is going to cancel for this, giving us 1 on top, but then we also divide by t plus 1, which means that this term is going to have a denominator of t plus 1. Now considering the other term as 2t, which remains as it is, we're dividing by t plus 1, so it cancels, but then we also divide by t squared minus 2t plus 4, which means we have 2t divided by t squared minus 2t plus 4. Now therefore we can say, if we integrate the left hand side, which is 3t squared plus 4 divided by t plus 1, I'll actually rewrite that with t like this, t plus 1 times t squared minus 2t plus 4, we can see this integrated with respect to t is the same as integrating these two terms individually with respect to t, which will be the integral of 1 over t plus 1 dt plus the integral of 2t divided by t squared minus 2t plus 4 with respect to t. Now we can see this is exactly what we wanted in the question. We wanted to find the integral of this term, which is now equal to the integral of this term and this term. So considering this, if we integrate them individually, the first term is just going to be equal to the natural logarithm of the absolute value of t plus 1. Since if we consider the term that we have here, taking the derivative of t plus 1 gives us just 1 plus 0, which is 1, and that is exactly what we have in the numerator. So therefore, integrating this term is quite simple. It is just the natural logarithm of the modulus of the denominator. Now considering the next term, we have 2t on top and we have t squared minus 2t plus 4 on the bottom. Now considering this, the order is 1 less on top than it is on bottom. So therefore we should be able to take a natural logarithm component out of this. But as we can see, if we take the derivative of the bottom, derivative of t squared is going to be 2t, which we have on top, but then we also have the derivative of minus 2t, which is going to be minus 2. The plus 4 turns into 0, so that's gone. So therefore, in order to take a natural logarithm component out, we need to have this term right here on top. So right now we can see we do not have this term. We instead have just the 2t. We do not have the minus 2. So what we need to do here is to introduce this term by subtracting 2 and then immediately adding 2 so that we don't change the value, but now we get the term 2t minus 2 on top. So what we're going to do here is to take this first result of natural logarithm of t plus 1, we're going to take it one line down, and then we're going to add to that the integral of 2t, and then we're going to add and subtract the same exact thing. We're going to subtract minus 2 and add minus 2 and divide it by t squared minus 2t plus 4 dt. Now note, this doesn't actually change the value at all. It's the same exact thing. It's just that we've now added minus 2 and subtracted minus 2 so that we can then remove the 2t minus 2 and write this as a natural logarithm term. So considering that going down, if we write this again, we can write this as natural logarithm of modulus of t plus 1 plus, and then what I'm going to do is to break this integral in two pieces at this point and write this as the integral of 2t minus 2 divided by t squared minus 2t plus 4 dt, and I'm going to write the other term as plus 2 divided by t squared minus 2t plus 4. So the integral plus the integral of 2 divided by t squared minus 2t plus 4 dt. Now considering the first integral we have here, we have natural logarithm of t plus 1, and the first integral is directly equal to the natural logarithm of the denominator, which is t squared minus 2t plus 4. We can see that by the fact that now if you take the derivative of the bottom, you get the top. So therefore we have this term, and then we also have this last term, which I'm going to write as 2 times the integral of 1 divided by t squared minus 2t plus 4 dt. Now, in order to turn this thing into a proper integral, what we need to do is to write it in the form 1 over x squared plus a squared, or 1 over x plus a or something like that squared plus b squared, like this, because then what we can do is use the tan inverse integral in order to find it more easily. So what we're going to do is to convert this integral into that format, and then we're going to write it in terms of what we know for the tan inverse. So if we call this integral I, let's say, and we take it down, we can see the denominator of I is t squared minus 2t plus 4. Now considering the first two terms, we have t squared minus 2t, which we could get by using t minus 1 squared. T minus 1 squared gives us t squared minus 2t plus 1. Now we can see we don't have that, we instead have t squared minus 2t plus 4. So what we can do is to write this as t squared minus 2t plus 1 plus another 3. So what I'm going to do is to take I down, and I'm going to write I like that. We're going to take I down right here and say I equal to integral of 1 over t squared minus 2t plus 1 plus 3, which is where the plus 4 comes from, dt. And I'm going to write this as the integral of 1 divided by, I'm going to write this as t minus 1 squared plus 3 dt. And I'm going to do one more step. I'm going to rewrite this again, but this time I'm going to write it as integral of 1 over t minus 1 squared plus root 3 squared dt. Now considering this, as we know, whenever we have this format where we have 1 over, let's say, x minus a plus b squared dt, the integral here is going to be equal to 1 over b times tan inverse of x minus a over b. So according to this, if we apply this to this particular case, we can see we have 1 over root 3 and tan inverse of t minus 1 over root 3. So considering that the integral here is going to be equal to 1 over root 3 times tan inverse of t minus 1 over root 3, and of course plus c. So therefore the integral I is that integral. Substituting that back into here, we can see we have natural logarithm of t plus 1, natural logarithm of t squared minus 2t plus 4, and 2 times this integral, which is 2 times 1 over root 3 times tan inverse of t minus 1 over root 3 plus c. So we can say finally, therefore, the final integral, which is the integral of 3t squared plus 4 divided by t plus 1 times t squared minus 2t plus 4 dt is equal to, and we can write the terms. First term is natural logarithm of absolute value of t plus 1. Second term is natural logarithm of absolute value of t squared minus 2t plus 4. And the third term is going to be equal to plus, and we have 2 times the integral, which is 2 times 1 over root 3 or 2 over root 3 times tan inverse of t minus 1 over root 3 plus c. And that is going to be the final answer to this part of the question. Now finally, let's discuss the marks awarded for this part of the question. So at the start of the question, when you use the fact that this equation is true for all t elements of the real numbers to say that the polynomial on the left and right are identical, and therefore all the coefficients must be equal to each other, and using that, when you create these three equations, for creating any two of the three, you get 5 marks. The reason it's only 2, of course, is because you only need 2 in order to find a and b. So for finding those, you get 5 marks, and after that, for using them to find a equals 1, you get 5 marks, and for finding b equals 2, you get another 5 marks. Now after this, when you then substitute a equals 1 and b equals 2 into your original equation like this, and then divide both sides in order to get 3t squared plus 4 divided by t plus 1 times t squared minus 2t plus 4 equal to 1 over t plus 1 plus 2t over t squared minus 2t plus 4, you get a total of 10 marks for these partial fractions. Now after this, when you integrate both sides and simplify all of the integrals, you get a total of 3 integrals and a constant term, which when you write out like this, for finding the first integral, natural logarithm of modulus of t plus 1, you get 5 marks. For finding the second integral, natural logarithm of modulus of t squared minus 2t plus 4, you get another 5 marks. And finally, for finding 2 over root 3 times tan inverse of t minus 1 divided by root 3, you get another 5 marks. And at last, for finding the constant term c, you get another 5 marks. It is very important that you write plus c, because this is of course an indefinite integral. Now in addition to this, they've also written a little sentence here saying that where C is an arbitrary constant, which you should probably write. However, they've only given marks for writing C. So always remember, whenever you have an indefinite integral, there's a high chance that they give marks for writing the plus C term as well. And it's of course important, since it is in fact a plus C term that we don't know. You have to write where C is an arbitrary constant, or at the very least, write that there is in fact a plus C in your integral. So with that, we're done with this question. I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching, and goodbye.